AP Chemistry Molar Conversions, the reaction table method. This is the method of choice for any time you're dealing with something that's at least two steps, or when you want to know more than one thing about a chemical reaction. Because when you set this up, it'll tell you everything that deals with grams and moles, and it's very convenient for limiting reactant problems when you want to see what's left over. This is how most chemists set up their lab notebook, and it's a handy tool. What you do is, for a given reaction where you want to know something quantitative, set it up like this. In this particular case, we're burning some butane, which we've done many times. Convince yourself those molar ratios are correct, and answer this question. The combustion, that means to burn 100 grams of butane, can make up to how many grams of carbon dioxide? The wording of this question tells you they're using excess oxygen. When they say up to, that means you can, if you have enough oxygen, make up to. Therefore, this plays no role in the chemical solution. I would recommend you set up your table, one column for each reactant and product, and determine the molecular weight. MWT means the molecular weight. In the case of butane, it's 58. Now we do need 2, and that'll play a role there, but right now we're just writing down data, the molecular weight of butane. 4 carbons means 12 times 4 is 58. I'm looking up the average molar masses, and I'm rounding from the periodic table. 10 times 1 added to that makes 58. 13 times 32 is not needed, it's just 32 grams per mole. 44 for carbon dioxide, 18 for water. Now, give them what you're given. That one little piece of data, from that everything else should spit out. How? Well, I can see that I have a little less than 2 moles here, right? 100 grams, where 58 grams is a mole, so I simply do grams over molecular weight to get the moles. I don't really do it that way. I've heard other instructors teach it that way. I simply say it out loud. If the molecular weight is 58 grams per mole, and I have almost twice as that, I must be dividing 100 by 58, meaning I have 1.72 moles. Now, I need 6.5 times as many, so I'll multiply that by 6.5 to determine that I need 11.21 moles to completely burn that stuff under ideal conditions. At 32 grams per mole, hey, that's more than 350 grams, I think. That'll be 358 grams, right? 11.21 moles at 32 grams for each mole. Multiply it through. Now I also determined that every 2 of these gives me 8, so I took 7.72 and multiplied it by 4 to get 6.90 grams of carbon dioxide are possible. I took, what did I do? Pentupled it, right? Times 5 to get 8.62 moles of water can be produced. If it's 6.9 grams per mole and 44 grams per mole, I will multiply those through to see that I could make up to 303 grams of CO2, and there's the number that answers the question, and I can make up to 155 grams of water. Now, we only needed that number, so you could consider doing a 3-step gram-to-gram conversion, which I've shown in a previous screencast. However, this tells you everything, right? This tells you how much oxygen gets burned, how many moles, how many grams, and it tells you everything. So ask yourself what the problem is asking and then choose the quickest method. This would be a great method if you need more than that. Let's do another problem. Very similar. Say we're burning 100 grams of magnesium. Draw a reaction table. Here's what you should be going through your mind. And by the way, I recommend that you pause this video, do it out, even though it's a pain, and then see how you did. 100 grams of magnesium, I'd write the balanced chemical equation, which is magnesium plus oxygen equals MgO, and there it is. Right? Mg plus oxygen makes MgO. Since oxygen is diatomic, you got to write it like that, and therefore it balances out 2 to 1 to 2. The only piece of data you're given was that 100, so that would be the next thing you'd write. You do know the molecular weights from looking them up on the periodic table. And where would you go from there? Well, I'd say I have a little bit more than 4 moles because I have 100 grams, but only 24.3 is a mole. 100 divided by 24.3 tells you that you are starting with 4.1 moles. You only need half as many moles to make your product, so you only need 2.05 moles. And you will make exactly the same number of moles of magnesium oxide. That's why these two numbers are the same. By multiplying by the molecular weight, you can get the grams that are involved, and that means that assuming plenty of oxygen, we have enough to make 165.3 grams of magnesium oxide. In our next screencast, we'll take a look at limiting reactants and see just how powerful the reaction table method can be.